Okay, hello everybody. This is the PowerPoint for class for Chapter 5, Section 1 on antiderivatives that I talked about in the announcement. So I will see some of you in a little bit in Blackboard, and what I'm going to do at that point is ask you what you think some of these derivatives are, and we're just going to think about it without any rules. So what an antiderivative is, or what the general idea here is we're going to, there's a thing called a differential equation. A differential equation is an equation that has a derivative as part of it. This has a derivative of part of this equation. Capital F prime of x equals 2x. What was capital F of x? And these are all written in that way. So in other words, you want to know what function has a derivative of cosine x. So actually, why don't we start there? Why don't we make that our first question? If I asked you what function had a derivative of cosine x, you would tell me. Is everybody talking to their computer now? Hopefully you're saying yes, sine x. Okay, D and E take a little bit more thinking, but if you wanted to know what function had a derivative of 2x, think about that. Right, it would be x squared. What function would have had a derivative of x? Well, this is where you think about, okay, I might have to get a little bit creative here and think about if I take the derivative of x squared, this comes down and the power decreases by 1, so I get 2x. So if I only want to get a 1x, I would have had to have taken this function, and I don't want to end up with that 2 when I'm done. So how could you get rid of the 2? Well, if you multiplied by a half, that would get rid of the 2. So 1/2 x squared would have had a derivative of x. All right. If you think about it, so would several other things. So would have x squared plus 3. Down here, so would sine x minus pi. Up here, so would 1/2 x minus e, right? Or minus e squared. Why is that? Well, because these are all just numbers, and if you take the derivative of a number, it's 0. The derivative of this number is just 0. The derivative of this number is 0. So what we do in general is find what's called a general solution of a differential equation. And how we indicate that is every place that I put in here a number that I just made up, we would make that a plus c. We would make this a plus c to indicate that capital F of x equals sine x plus any constant, which could also be negative, gives you cosine x. All right, again, like I said, we would take a little bit more thinking. What you would have to do here first is think of this as x to the negative third. And then once you thought of that as x to the negative third, then we could say, what would have had a derivative, because this is the derivative, what would have had a derivative of x to the negative third? Well, once the power went down, it would have become a negative third. So we must have had an x to the negative second to start with, right? But if you just take the derivative, let's think this out, of x to the negative second, you get x to the negative, you get negative 2 x to the negative third. But there is no negative 2 over here. And we don't want, how do I want to put this? There's no negative 2 over here, and we don't want the negative 2 over here. So you would have had to multiply by a negative 1/2. Negative 1/2. And then finally rewrite that as negative 1 over 2x squared. And then I guess we would want to have, even in this step, but I'm out of room now, we would have not wanted to forget the plus c. Okay, so like I said, these take a little bit more thinking, and in one of these lessons where I don't have anybody to interact with, I'm just kind of giving you the answers. But as we go through, if you want to give yourself time to try these problems yourself first, by all means do that. One thing I will say is pause here. All of these formulas are in terms of x. On your formula sheet, they're all in terms of u, because you're going to learn something later called u substitution. And with u substitution, you would see something like the integral of e to the u equals e to the u plus c, and that's going to make sure that you understand what type of substitution to make. But I think it's really pretty nice in section 5.1 that they don't talk about anything in terms of u yet. So you just get to see right here that one of the problems that you did, the integral of cosine x, is sine x plus c, and you don't always have to think backwards. In other words, you know that the derivative of secant is secant x tangent x. So if they give you the integral of secant x tangent x dx, and we're just going to say that's secant x. By the way, I didn't mention that as far as antiderivatives go, we're going to use the same notation we did with areas, but we're not going to put a number here and here. What's different now is this is called an antiderivative. So the antiderivative of, or actually, we could call this an indefinite integral, where when you had the numbers, those were called definite integrals, and instead of giving you a function, it gave you a number for your answer. So pause this if you want to write any of these down or take a picture of it, because you're going to be using these formulas as we go through and do some examples. So here are some examples, and I really do like this table, so I'm going to start down here. What we did on the first page were kind of like these. To solve these differential equations, you want to find the general solution of the differential equation and check the result by differentiation. Well, yeah, these are ones where those formulas might come in handy. So if you want to know what had a derivative of x to the 3/2, or let's go back to this one. This one's pretty similar to what we did before. What had a derivative of 2x to the negative third? Well, we can use the formulas from the last page and say that the 2 is a coefficient, so it just kind of hangs out, it stays there. And then we're going to do x to the 1 higher power over that power, which becomes, since the 2's cancel, this becomes a negative 1 over x squared, because this negative sign could go anywhere. This negative sign could go in the bottom, come out front, go to the top, it doesn't matter. And if you want to check by differentiation, you can always check the answer. What would have been the derivative of this? Well, the first step, I hope, if you were finding its derivative, would have been to write that as negative x to the negative second, and then use your power rule, and the derivative would then be positive 2x to the negative third. And if you look at this original question, it is positive 2x to the negative third. All right, so this is your answer, and this is your check by differentiation. So what I want you to realize is that in this particular example, the way that they gave you the problem isn't the way you normally see things written. Typically, you don't see things given with negative exponents. You might have to rewrite them that way. So I'll use number 8 to start with. If we want to integrate this using the formulas, and by the way, if you didn't see it, we just used our main theorem, which was this one, or our main basic rule of integration or anti-differentiation. When you have x to a power, you want to increase the power by 1. This is the opposite of differentiation, opposite of taking a derivative. So you want to increase the power by 1. And then to make up for the coefficient that would have been present in its derivative, you have to divide by that number. So x to the n plus 1 over n plus 1. And then don't forget your plus c. Did I forget my plus c in that last one? I'll be darned I did. All right, so this should have had a plus c at the end. All right, so for our rewrite step, this would be written as, we can take the 1/4 and take it to the outside. If you're not sure why, there actually is a property right here that says if I have a coefficient times a function, I could pop that coefficient to the outside and just worry about the part that needs a formula. So the part that needs a formula here is going to be this 1 over x squared. okay, the fact that we have an x squared in the denominator. So I want to pull that up to the top. That's my rewrite step. Then I'm going to integrate it. When I integrate it, I'll do it in a different color so in case they all run together, I'm going to get 1/4 x to the 1 higher power over that power plus c. It says a -1 up there. And then when I simplify it, the reason for simplifying is in all of these kinds of problems where you usually need a rewrite step and then you integrate and then your answer is usually in a form that's really technically not simplified, and it's not a form that you would want to leave your answer in. So this is kind of a mess. And we want to take this, because it's raised to a negative exponent, and move it. We usually want to move negative signs out to the front or to the top. So finally, my last step would be this equals -1 over 4x plus c. Okay. Something like number 9, I usually save you odds, but you won't have this one as one of your problems. So this will combine what you've done here, plus we'll have some negative exponents. Actually, you know what? We haven't done any positive exponents yet, I don't think. So maybe we should try this first. Okay. For a rewrite step for this problem, I would want to write that as the integral of x to the 1/3, right? We would want to take our radical notation and change it to a rational exponent. So then we can integrate it, which would be x to the 1 higher power. So 1/3 plus 3/3 gives you 4/3. And then over that power. So that would be over 4/3. All right, if you can't read this, this says x to the 4/3 over 4/3. So what do we do with that? Well, you take the top times the reciprocal of the bottom, and then that gives you 3/4 x to the 4/3. And again, you could totally check these with differentiation. If you took the derivative of this, when you pulled the exponent down and multiplied by this coefficient, it just disappears. And it's just x to the 1 less power, which is x to the 1/3, which is what you have right there. All right, last thing as far as rewriting. To rewrite this, I'm going to move it down a little since we're not going to do number 10. This would be the integral of, well, let me think about it right here. This is x to the first times x to the 1/2. So you would add those exponents, and it would be x to the 3/2. But now when I pull it down, or when I take it from the bottom up to the top, that would be x to the -3/2. Okay, so now you take x to the -3/2 and integrate. Using that power rule, we have x to the 1 higher power over that power. And when you simplify, you take the top times the reciprocal of the bottom, and you get 2x to the 1/2. And as much as this is fine, a lot of times when you have an exponent of 1/2, you might just want to write it as back in the radical notation. If it's 3/2 or 1/3, well, not 1/3. I guess when this isn't a 1, you typically want to just leave it as a rational exponent. But if this is a 1, a lot of times you will see this rewritten using radical notation. All right, what else can we do with these antiderivative rules? I just want you to see that a lot of times there are things to do to simplify your function first. You cannot, or you can, but you won't be right, you can't take the antiderivative of the top and put it over the antiderivative of the bottom in an answer. Because just like you had a quotient rule for derivatives, you can't just simply take, but you couldn't just take the quotient of the top and derivative of the top and derivative of the bottom and write them out as if that were the answer. The same thing goes with integrals. But there is no quotient rule for integrals, so you're just going to have to figure out, how can I simplify this? Some people like to simplify this. Now, some people, in this case, is not me, but it could be you. They would like to take the x to the 4th and bring it up as an x to the -4th, and then distribute through. Okay. Other people this is me, likes to sort of split this up. So I would have x to the fourth over x to the fourth, and then minus this term over x to the fourth, and then plus this term over x to the fourth. Again, or you can distribute the x to the negative fourth through each one of these, adding the exponents each time, and no matter which way you think of it, this simplifies and gives you the integral of 1 minus 3 over x squared plus 5 over x to the fourth. And then we can integrate that as long as we rewrite the second two terms as 3x to the negative second plus 5x to the negative fourth. And then finally use your integration rules, and you would get the integral of, the integral of 1 is just x. The integral of this term, let's let the coefficient hang out, it would be x to the 1 higher power over that power. And then 5, x to the 1 higher power over that power. And then let's clean it up. X, a minus times a minus gives you a plus. A plus times a minus gives you a minus. And those x terms, because they had negative coefficients, have to move to the bottom. Alright, and that's how you do these problems. So let me just talk about a few of the other ones, because I only have one of these slides. Here this would be, what, theta cubed over 3 plus, and then you have to look up the formula for what is the antiderivative or integral of secant squared theta, and it is tangent theta. Right? So you have theta cubed over 3 plus tangent theta plus c. Here you would want to distribute this through first, secant y tangent y minus secant squared y. And you have integration formulas for both of those. Lastly, number 30, if you're trying to integrate, say, 3 to the x, let me show you where you will find that. If you want to integrate 3 to the x, it would be 1 over the natural log of 3 times 3 to the x plus c. So no matter how bad they look, please remember they're not that bad. This is the one that you want to pay attention to the most. If you ever see, say, 1 over x, and you try to rewrite that as x to the negative first, and then use this rule. The integral of x to the negative first would be x to the 1 higher power, right, x to the 0 over 0. So do you see why they say but n can't equal negative 1? So you can't integrate. That's the one expression where you don't want to rewrite this using negative exponents, is if the denominator is raised to the first power. If the denominator is raised to the first power, we're going to have the natural log for our answer. And we have to restrict the domain at this point because this x could have been positive or negative, but do you remember with the log function, its domain is just greater than 0. Okay. This is a neat thing to think about, and we might be able to get to this in class and collaborate. They just want you to sketch graphs of functions that have the given derivative. So if you had a derivative, say, of 0, a derivative of, what would this be? 2, 3, 4, 5, 6. So this is 4. What would always have a derivative of 4? Well, a line that has a slope of 4, right? So I could go through the origin and go up 4 over 1. That would have a constant. I didn't mean to do that. A little wrist guard here. That would have a constant slope of 4, so that's one solution. But I could move that line too, right? I could shift that line down. That always has a slope of 4. I can shift this line up. This always has a constant slope of 4. So this is actually called a family of functions that all satisfy the differential equation f prime of x equals 4. Okay? Or if dy dx equals 4, then y just equals 4x plus any constant. And graphically, all those solutions look like this. So, I mean, we could talk about that for a ton of time. You know, this would be what? X. This is the line y equals x. So this is where you have the differential equation dy dx equals x. So what would y equal? We'll use your power rule. And that would give you another family of curves, but those would be parabolas. They would be wide parabolas. So you can have one that goes through the origin, one that's a little higher, one that's lower. Any of those functions where you put in anything for c, those are graphs of functions that have the given derivative. All right, so I have 3 more things here to look at. If you want to try them yourself first, maybe at least after we try 36, then you can try 40 and 42. Okay, so this is written in a little bit of a different way. This says that f prime of s equals 10s minus 12s cubed, and they give you something that's called an initial condition, because this is what takes your possible answers from being a whole family of curves to just one specific curve, and it would be the one curve that would go through this point. Alright, so if f prime of s equals 10s minus 12s cubed, then f of s would equal, I need to take the antiderivative of each one of these terms. So this would be 10 times s squared over 2, which hopefully now you would just be able to cancel the 10 with the 2 in your head and say 5s squared. And then we'll do the same thing for minus 12s squared, or I'm sorry, minus 12s cubed, so that'll be minus, and let's just think this out loud and see if we can cancel this without writing everything down. So this part would be s to the 4th over 4, and then the 12 and the 4 would cancel. So then we would have minus, 3s to the 4th. Now, don't forget your plus c. If you forget your plus c, then you won't know what in the heck to do with this, right? But because they tell you that f of 3 equals 2, then we can plug we could plug a 3 in here. 9 times 9. Okay, and then we have to set that equal to 2, and that's going to let us, because they told us that it equals 2, and that's going to let us solve for c. So it is it's 45 minus 243 plus c equals 2. 198, negative 198, and then we add, I guess I don't need to keep writing these equal signs. Negative 198 plus c is 2, so c is 200. So your final answer for this problem is f of s equals 5s squared minus 3s to the 4th plus, now I can plug that in for my c. And this is a function. I would highly encourage you to pause the video and put this into your calculator and graph it, and then you could do this other thing where if you put this in as y1, then for y2 you can first trace, use the trace or evaluate, but I would say use trace the function at 3, and notice that you do get 2, okay, if you trace this graph. And the other thing is, if you, and this is a lot to try out on your calculator, but it's really neat for understanding. If you let that be y1, and then you let y2 equal math 8, which for some of you is nderiv, y1 with respect to x at all x's, or for other people it's going to be d box, and you're going to fill that in with x, of box, and you're going to fill that in with y1 as x equals box, and then you just fill that in with an x. If you plot this as y2, and then last for y3 you plot the original function that they give you, these two should be the exact same graph. They should plot one on top of each other. And if you can't see them come up in different colors, if you don't have a color calculator, then take the equal sign for this one after everything graphs and turn it off. Hover over it and hit enter, and that'll turn that one off. And then you'll see that this graph is the exact same graph as that one. So it's pretty cool. Alright, let's do two more. Number 40, what if your second derivative is sine x? Then, and notice they're giving us a second derivative this time. So if the second derivative is sine x, then when we back up, we're only backing up to f prime. So f prime is, you can use your formula chart, but it's negative cosine x. And no, you're not remembering things wrong. If you thought it was positive, you might just be thinking derivatives. And I always say that's thinking in the wrong direction. So now let's say f prime of 0 is negative cosine of 0 plus c, and that equals 1, because it says it equals 1. Well, cosine of 0 is 1, so negative 1 plus c equals 1, or c equals 2. So let's rewrite f prime of x as negative cosine x plus 2, right? Because for c, I'm plugging in what c is. Now I still have to solve, because they want you to solve, find the particular solution. That means find f of x. So what had a derivative of negative cosine x? Negative sine x. What had a derivative of 2? That would be 2x. Don't forget your c. This is a new c, represents something different than the other one. We're just kind of reusing that constant. And now we have to solve for this c. So let's use the other initial condition. Negative, how about if we just, instead of writing it, I'm plugging in 0 for x. Okay, so negative sine 0 is 0. 2 times 0 is 0. Plus c equals 6. So you can see that c equals 6. And then plug it back in for c to give your final answer. Negative sine x plus 2x plus 6. Okay, and if you want to try 42 on your own, go ahead and pause and try it. Okay, I'm about to work it out. Now we have to take the original f double prime and do a rewrite so that we can use our power rule. Alright, so f prime of x is 2 times x to the 1 higher power over that power plus c, or negative 2 over x plus c. Now we know that f prime of 1 means we're going to have negative 2 over 1 plus c has to be equal to 4, because that's what they say. So that gives us c equals 6. And then let's put that into f prime. Negative 2 over x plus 6. But to find my next function up, I'm probably going to want to think about this as negative 2x to the negative first. Okay, so now let's back up one more time. So f of x equals negative 2 x to the 1 higher power over that power. And then you go, oh, wait a minute. Maybe I should have not used this, but kept it this way. And then maybe I would have realized that I should be using the other formula, the one that we use when the power is negative 1. So it's just the natural log of x, and then the antiderivative of 6 is 6x, and then we're going to reuse the c, so we have another c here. Alright, now let's use that fact that f of 1 equals 3. So f of 1 equals negative 2 times the natural log of 1. It's already positive, so I don't have to write those absolute value symbols. Plus 6 times 1 plus c equals 3, because it says it has to equal 3. And hopefully you know without a calculator that the natural log of 1 is 0. So 2 times 0, or negative 2 times 0 is 0. So then we just have 6 plus c equals 3. Subtract the 6 from both sides, and c equals negative 3. So your final answer is f of x equals negative 2 times the natural log of the absolute value of x plus 6x minus 3, which you can take the derivative of twice and check to make sure you get that answer. Okay, the last thing to talk about, but I don't know if we want to go over it now or some other day in class. Oh, what the heck now, right? You can watch the whole video, or you can pause and save this for another time. But vertical motion, we learned equations for these before, so that's why I have this written on here already. For free-falling objects, when we're talking about feet instead of meters, this number, which is half of acceleration due to gravity, is going to be a negative 16. If we were talking about meters, this would be negative 4.9. So I wanted to look at number 54. 54 says, with what initial velocity must an object be thrown upward from the ground to reach the top of the Washington Monument? You'll want to pause a lot to try things on your calculator if you want to work through this with me. But, and the first thing that you should pause to think about is, what can we fill in here? What can we put in for your initial velocity? What can we put in for your initial position? And when you're done thinking about it, come back and see how you did. Okay. If you were thinking you were going to put 550 in for your initial velocity, that's a good thought, but that's not going to be, for your initial position. It's a good thought, but that's not your initial position. That's where you want to end up. And also, we don't know the initial velocity. That's actually the question, with what initial velocity? So from here, what can we do? We could say that we know we want our position to equal 550 feet. So we can say 550 equals negative 16t squared plus your initial velocity times t. But now we have one equation with two unknowns, and that doesn't help. So what else can we do? Well, when all else fails, just, what can you do from the position? Well, you can take a derivative, and that gives you your velocity, right? And that function would be, or that derivative would be negative 32t plus your initial velocity. So now you know a couple things. You know that when the maximum height is reached, picture this thing going up. You threw something, and it goes up, and then it has to stop, and then it comes back down. When it stops, you not only know how high it needs to go, but you also know that its velocity, you want your velocity to equal 0. Okay. So let's set the velocity equal to 0. And that gives you that v sub 0 equals 32t.